Okay, welcome back to round 2 of our videos for the day. Hopefully things work out all right. I think that it paused my video when I had a weird face going on, so that's gonna be real cute in the first video. And then my internet has not been fully working to its best abilities. So it's been real fun trying to record and upload these without any issue. So hopefully we can continue on without any issues. Oh, it's been a very Monday of a Tuesday, but that's okay. So to continue on for the videos for today, we're gonna finish up talking about a couple of different adaptations that creatures have to learn to adapt to, or various techniques or things that creatures have to adapt to. And then we'll jump into different types of plankton, some of my absolute favorite creatures of the sea. So with that, no further ado. So we already talked about adaptations for light, temperature, and salinity, which are all kind of larger sort of sections, I suppose. But we also have to consider that there are creatures that have to adapt to pressure, right? So for every 100 meters of depth, the pressure in the water increases by 1 atmosphere. So we know that pressure increases with depth as we go down. We've talked about that several times throughout the semester, but a unit of pressure that is often used is atmospheres, similar to like pounds or kilograms for talking about weight, things like that. So atmospheres are used as a unit of pressure. But we know that water is pretty much incompressible. You can't like take it and like smash it down. You can do that with air very easily, but you cannot do that with water. But marine organisms are mostly made out of water. And so there's really, in all its entirety, not a huge issue here. Unless you are a creature that has swim bladders or lungs. And if you have a swim bladder, one adaptation that their body has is a fatty wax that surrounds the swim bladder to protect it from the harmful connotations of pressure that it could have on it. And then with lungs, there's lots of marine organisms out there, or marine mammals out there, that do a whole heck of a lot of diving. Whales in particular, right? If we think back to our friend, the sperm whale, who hangs out near the surface and then takes a big old breath and dives deep down into the oceans, anywhere from 3,500 to 4,000 meters, down to hunt for giant squid, their lungs are going to compress as they go down. You can see this with the humans too. If you ever watch free diving videos of some of the people that go like super far down, you can see that like it looks like their stomach is being kind of sunken in a little bit, and that's because their lungs are shrinking, because the air that's in their lungs is being compressed. It's actually super dangerous for a free diver to accept air from a scuba diver if they're both down in the depths together, because if they accept that air and if they go up, then the air that's already in there, which expand their lungs back out, can expand even more and can be deadly. They actually teach you that when you're getting free dive certified. That is a big no-no, even with scuba diving certification. I think they told us to don't share your respirator with anybody else. Anyways, so creatures have to deal with that. And generally, organisms that are in the greatest depths use various compounds in order to protect their proteins in order to function properly. So we know that the deep ocean has remained rather homogeneous for a long time, right? There hasn't been a whole lot of disturbance there. So the animals have been able to evolve very well to that environment. And so the proteins in their body cells have evolved to be able to withstand that. And the problems that occur is when animals are forced up the water column for way too long, in way too short of a time, and then that can allow for the cells to expand and perhaps explode, which is kind of what we saw with blobfish, right? Those poor little nuggets. Cool. So it looks like my camera failed on me again. So this is awesome. Sorry if that's the case. If you like looking at my face during this, I don't have any control of it. My computer is just, it's being real annoying. Anyways, so moving on from pressure, we have buoyancy. So this is mostly an adaptation for some of the smaller animals on our planet, aka plankton. So buoyancy, though, is whether or not an object floats or sinks, which is determined by the balancing forces of gravity and their buoyant force. So, like, for example, like pufferfish, when they poof up, when they are agitated and they poof up, they are pretty much forced to float because now they have way more air, which makes them lighter than the environment around them, so they would float up to the surface. But plankton in particular, which your book kind of hones in on, some of them can store oil drops in order to decrease their density, or some have various appendages that help increase their surface area so they can expand out and then float up to the top, which is really quite fascinating. These are some examples here. So we have some diatom chains. See how they have like these almost like weird legs kind of protruding out, or this copepod here, which the little antenna almost look like little ferns, right? Or even some of these larvae that have little extra appendages on them too, which will help with their flotation as they go through their juvenile portion of life. And some of these creatures can also like retract and expand their limbs so that they can either sink down the water column during the day to nutrient-rich waters, or expand them out so they can float up towards the surface and get sunlight, right? So remember that plankton are floaters. They don't have any wherewithal to move on the horizontal, but they can adjust themselves to move in the vertical, which is often what we see. And then inorganic nutrients. This is the last little bit of adaptation that we're going to talk about, because we already talked about dissolved gases and pH levels. But inorganic nutrients, we know that autotrophic creatures use inorganic nutrients to help them grow. They use sunlight, which is huge, right? They need that sun, but they also need other nutrients in order to help them thrive and survive in large numbers. And what we see is blooms. And a lot of this can come from nutrient runoff from land and also regions of upwelling. So we've talked about upwelling several times in this class at this point. Remember, it's where Ekman transport takes water out from the shoreline. So cold, nutrient-rich water has to replace that water, which is filled with nutrients from the deep ocean. And that can then allow for plankton to be like, oh my goodness, that's so delicious, num, 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 num. Or when we have rivers flowing into the oceans, which can be helpful there. All of this put together can cause phytoplankton blooms, some of which can be harmful, and we'll talk about harmful algal blooms later on. The way that you can kind of remember this idea is, even us as humans, we can't eat cheeseburgers all day, every day, and hope that we're going to be a healthy human, right? We have to have, as great as that would be, not necessarily the best course of action into being a good, healthy human. So we have to get nutrients from various sources. Like I take a greens drink in the morning. I have my protein smoothie, and then I can even snack on things here and there, right? But I'm getting my nutrients from multiple sources, not just from one source. And that's the idea with this one here. Okay, so when we're considering all of these things, all of these adaptations, it's a big thing to remember that size matters here. So the oceans, which is wild, the oceans contain the smallest and the largest organisms found on Earth. The larger the size, the lower your abundance. But the smaller the size, the higher your abundance. So that's what this graphic here on the right is trying to show here, where we have viruses and bacteria, which are on the order of micrometers and nanometers. So really, 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 really tiny. Then we have microplankton, small zooplankton, large zooplankton, and then of course the overall just large animals in general. So we have way more concentrations of these really small creatures and less concentrations of these really massive creatures. And so that can kind of help, kind of give us a sort of idea of where we are at. So some of these smaller zooplankton, they are actually the juvenile part of some of these larger creatures, and a lot of them get eaten or die in some way, shape, form, or another. So if they were all to grow, if they were all to survive and go into the massive, large animal adult stage, then the oceans would be completely overrun. So there's a reason why these smaller creatures have a much larger abundance. I think with that, we'll go ahead and stop here, and then the next round of videos, we will jump into different types of plankton. So this slide here wraps up chapter 11. So be sure to chip away at that smart book reading assignment. And again, so sorry that my camera does not want to cooperate today. And technology just in general is not being my friend. So hopefully we can fix things hopefully at some point, but we'll see. So thank you again so much for listening and your attention, and I'll see you soon.